Okay, hello student. Today we have an example on the statically indeterminate rigid frames as shown below. This frame have two columns and one beam. This frame has the modulus of elasticity of 205 gigapascal. And if you may know, if you like to use the kilonewton, the 205 10 minus 9 Newton per square meter will change it to 205 10 power 6 kilonewton per square meter. And the beam has the moment of inertia of 2I, and the column has the moment of inertia of I1. So the beam gonna be 2 times moment of inertia with respect to the column, and this one supposed to be 67.510 minus 6 meter power 4, not this one. And they asked us to determine the reactions. We are going to have the reaction at D. The D is the pin. Okay, so we supposed to have both D sub X and D sub Y. And also at the A is a pin. Okay, we have one, and we have this one is the A sub X and the A sub Y. So actually we have the total of four unknown reactions, and our structure gonna have one free body diagram with 3 equations of equilibrium. So this problem going to have the degree of indeterminacy of 1. So we're going to have one redundant force based on the consistent deformation. Okay, we need to have one redundant force. And the problem said they're going to provide that with the horizontal force, at D as the redundant force. So this one is going to be the redundant force. So based on this, what we have is we going to put the D sub Y into this. And since we put D sub Y into this, what happened is the support, when you put this, the support will change from pin at D to roller at D. So if you put this, the A is going to be the same. The A is going to be the same anyway. Okay, but the D will change to the roller. Okay, the D, and then what we have is under this frame will separate into 2 frames. So first one we separate the frames into 2 cases based on the principle of superposition. So this time we change this one into this one. Since you have D sub X, this support will change from the pin to the roller. Okay, and then what we have is the structure gonna have this deformation plus another one, but this one will subjected to the redundant force. So Basis on this, we got two frame. Is the primary frame that is subjected to the given loading. Okay, and another one is the frame. Subjected to the redundant force d sub x. Okay, is going to have two of this, and basis on this deformation is going to deform under the application of the giving load of 2 kilonewton per meter. Okay, they're giving us the structure gonna have the deformation in this direction of 0.963. You may calculate this if you like to do so. This is 0.963. But for this one, let's put the d sub x into this direction. It's subjected to the d sub x. Okay, so this is going to move inward into this position, and what we have is the deformation in this direction, and usually we will set the d sub y into 1, and this is going to be f sub d, f at point d, due to the applied force at point d, so it's going to be f sub dd. And if you like prefer, you may set this one will move this way, and to keep this as the right angle, this one gonna move something like this, and this is going to put in right angle and have the deformed shape like this. Okay, and second we will have the compatibility at d in the x direction. Okay, so you got to refer to basis upon the deformation of the frames. Okay, 3 of them. We may set the deformation in this direction is plus. So what we have is this one, even though it's changed from the pin to the roller, the d sub x gonna hold this, and basis upon previously know this is gonna have 0 displacement in the x direction at d. And for this, you're going to get is for 0.960 millimeter in this direction, if this one is plus. And this one gonna be minus what? F sub dd, and then d sub x. And now your d sub x gonna equal to what? 0.960 millimeter, and divided by f sub dd. Okay, that is going to be our compatibility equation, and based on this compatibility equation, after we determine f sub dd, we can find the redundant force of d sub x. So our next step, the third, we find the force displacement relationship. Okay, that is going to be f sub dd by using which method you prefer. You may prefer the method of virtual work, or if you like, if you read the textbook, the author textbook, you may use the classical theorem if you like. Okay, this one we use the method of virtual work. It have the nickname of unit load method. Okay, and if you basis on this, what you have is the virtual work equation. Okay, we have virtual work equation. The virtual work equation said the external virtual work is going to be equal to the internal virtual work. And what is going to be this one? The external virtual work. You got to have another frame this time. And what happened is your frame gonna subjected to a virtual force or the assumed force of 1 unit. Okay, so it's going to subjected to the 1 unit. At what point? The 1 unit supposed to act at D. Okay, and in the same direction as the movement. This one in this direction. Okay, that is going to be 1.0. And again, you will have this one going to be F sub dd, right? Because we cannot compute it directly, we got to set the ed sub x equal to 1. So this one is F sub dd, and the total of this is going to be F sub dd d sub x. As you have this, and that is going to have F sub dd. Okay, F sub dd, and then it's going to be equal to the internal virtual work. This 1 unit gonna produce the moment m inside this one because it's going to bend. Okay, this frame like this is going to produce the moment. So this is produce moment m. If this one subjected to the d sub x, the moment supposed to be capital M. But this time you determine this, you set d sub x equal to 1. So this m, capital M, will change to the small m. So now, the deformation here, as you may know, the d theta equal to m and then dx over ei. That is the change of the shape of this frame when d sub x equal to 1 due to the moment small m. So when you put this one going to be m square and then dx over ei. Okay, and then you do the integration because the deflection is the continuous function of this. Okay, now our problem reduced to what? To determine this moment m. After we determine this equation of m, we can determine the f sub dd. So we find the moment equation m. Okay, and before that, let's mean we're going to put this one. Let us put this frame into this area. Let's put this one for 4 meter. 4 meter is 2 centimeter. Okay, that is 4 meter is 2 centimeter. That is going to be 3 meter. That is going to be 1.5. Okay, and this is 2 meter. This is going to be just 1 meter. And this frame subjected to 1.0 force. So this frame subjected to 1.0 unit force. And again, if you put the moment here, you will see the force here going to be in which direction? The moment here gonna put this way. Okay, that is going to be counterclockwise. So the force here is going to be d sub y, going to rotate clockwise to balance it. Now the force here going to be in this direction to balance with this. So this is going to be a sub x. And you also have this one. This is downward. So this one this one gonna be upward of a sub y. So this one is 4 meter, this one 2 meter, this one 3 meter, and this is A, B, C, D. And then you do the summation of the moment at A first, at A equal to 0. This is going to have the counterclockwise direction. So this is plus. We have this one, have the distance from here to here. It's going to be the moment arm of this. It's going to be 4d sub y, 4d sub y. And this one gonna rotate in opposite direction, and the distance here gonna be 3 minus 2. So this is going to be equal to 1 and time this one of what? Of 1. And then you have the d sub y equal to d sub y equal to 1 over 0.25. Okay, you may say it's going to be here of 0.25. And then it's going to be easier, just summation of x sub x equal to 0. So this a sub x is going to be 1.0. And if also you put this one is positive, summation of f sub y equal to 0. So this one you got to put upward is positive. Okay, so this a sub y gonna be equal to d sub y of 0.25. Now we're going to set, to determine this, set what to thing, set the coordinate. Okay, and then we have 3 of them. So we got to set, let's say this one is the x1. Okay, and this one is going to be the x2. And please set this one as the x3. Okay, Ajahn, can I set different from you? It's up to you. Okay, everybody has a chance to set. But if you set it, okay, you're going to do the same way as for different m's. Now you may cut this. Okay, for this and this one, and also for this one, for the free body diagram. So we have this one for the first portion of this, and this is gonna be for the x1. Okay, this one from here to here, and then we have 1.0 and 0. This is going to be 1.0, and this is going to be 0.25. That is going to be the moment of small m1. Okay, and then we have further into this, and then it's cut here. That means it's going to move from here to here. And what we have is we're going to set this one for the x2. Okay, and what we also have, this one is going to be 3 meter. And again at the A we have this one for 1.0, and this one for 0.25. And now we are going to determine the M2 for this. And the last one, you got to project this one up here, and you have this portion of this one. And then this one subjected to the force of 1.0. And this one is downward, 0.25. This is going to be 0.25. And this is going to be x3. Okay, you can do that easily. And then you put the m3 over here. This is going to be for the small m3. Now, if you like, you may see this one, summation of the moment equal to 0. Take the moment here. We didn't put shear and the axial force here because it's going to make thing mess up. Okay, and the 0.25 have produced more moment. It cut this one, but this one going to produce the moment, and since it's moved in the same direction as M1, so this one gonna be 1 time x1, so 1 time x1. That means it's going to be in the negative, right? So it's going to be minus x1. It's going to be minus x1. To be minus x1 for this one. Okay, and then you move further to this one. Just take the moment here. Okay, summation of the moment equal to 0. Take the moment here. What we have is our M2 is in this direction, and what you have is the 1.0 gonna move in this direction. Okay, so you have M2 plus 1.0 gonna time this distance of 3, okay, time 1, okay, and then 0.02 gonna be in this direction and going to be in opposite, so it's going to be equal to 0.25, and then it's gonna time x2. It's going to be equal to 0. Okay, so now this one is going to be minus 3, and plus 0.25 x2. Okay, let me mark this one for the x1. Marks this one for the M2, and the last one, if you do this one, you just to do the summation of the moment at this point equal to 0. So this one produce 0 moment. This one going to produce the opposite moments of M3. So this one gonna be time what? X3, right? So this one X3, and then you may put this one for this column. Okay, we have all the moment for this equation. Now we just put all of them into your equation. So this is going to be equal to, the first one is here, integration from what? From A to B, from 0 to 3, and this one is going to be minus x1 square, and then it's going to be dx1 over ei1. Okay, and then we move to plus the second one from B to C, integration from B to C, from 0 to 4, and your equation is here is minus 3 plus 0.25 x2, and then it's going to be square, and now it's going to be dx2 divided by 2ei1. Okay, and the last one is here plus the integration. This time you integrate from here to here, from 0 to 2, and this one gonna be x3 square, and then you do the integration of dx3 with respect to divided by ei1. Okay, and you got to do it carefully, and if you do it good, you're going to get this one for 24.333 divided by ei1. Okay, and then you come to this equation is in millimeter unit, so you got to do some calculation. This is going to be 24.333, and then divided by, if you go back here, this one and this one, okay, divided by 205 10 power 6, 205 10 power 6 kilonewton per square meter, and you also have 60 67.5 10 minus 6 meter powerful. Okay, and then you get this for 1.758 and 10 minus 3 meter. And since it is positive, okay, that means it's going to be in the same direction of this. So F sub dd going to put from the right to the left. So it's going to be this one. And in the millimeter, it's going to be 1.758 millimeter. Okay, now we are ready to determine the redundant force. Okay, if you put this one and then coming to this 1 2 and 1 2 3 and 4 compute d sub x and determine the reaction of the frame. Okay, so this one gonna be easy. Our d sub x is here, so d sub x equal to this one 0.963 is gonna be 0.963 millimeter, and then it's gonna divided by 1.758, so divided by 1.758 millimeter. Okay, so our d sub x gonna be equal to 0.547 kilonewton. This is going to be equal to 0.547 kilonewton, and you can see, if you know this, the other reaction, we can determine it easily. Okay, now we arrive at this of d sub x, and we are going to determine the reaction. We go back again to this structure. Okay, we do the same thing. This one is 4 centimeter. Just put this one. Just put this one is 4 meter. Sorry, 4 meter. And this one is for 3 meter, and this one is for 2 meter. And the force that act on this frame is going to be 2 kilonewton per meter, and we have this redundant of 0.547 kilonewton, and what we have is the reaction at this point d, that is going to be d sub y, and you also have this point of a. We are going to determine the a sub x, and also we are going to determine the a sub y. Okay, and it's very clear again, this is going to be 4 meter, 3 meter, and 2 meter. You do the same thing as before, summation of the moment at A, okay, at this A, equal to 0. Again, your d sub y gonna rotate counterclockwise, so this rotate counterclockwise is positive. The d sub y gonna time this 4 meter, so it's going to be 4 d sub y as before. Okay, and what we have, this one gonna rotate by this as before. This is 1 meter, and this guy gonna rotate in the same direction as d sub y, so you gonna plus, okay, 1 and time 0.547, and then you have this. Okay, this is going to be 2 times 4, that is going to be 8 kilonewton, and this is going to be 2 meter. Okay, and this is going to be rotate in opposite direction, so 8, and then it's gonna time 2. Now you plug everything into your calculator, you will get d sub y equal to 16 minus 0.547 and divided by 4. It's going to be 3.863 kilonewton. Okay, and then this is going to be our d sub y of 3.863 kilonewton. And then just do the summation of x sub x equal to 0. So this time is going to point plus. So our a sub x just in the opposite of this. So a sub x is going to be 0.547 kilonewton. Okay, and the last one, you do the summation of f sub y equal to 0. Now this one is upward. Okay, our a sub y, put this a sub y plus 3.863, and then it's going equal to 8. So our a sub y is going to be just 8 minus 3.863 is going to be 4.137 kilonewton. That is the reaction of this frame. Okay, 4 of them. This is a sub x equal to d sub x, and this is d sub y. This is a sub y, and now we are ready to draw the shear diagram and the moment diagram of this frame. Okay, so we got to separate each segment of this frame, and we will find the end shear and the end moment, and later on we will find the shear diagram and moment diagram. Let's see. This is 3 meter. Let's plug this one into this size and set this one is 3 meter. Is going to be A, B, and 3 meter. And you're going to put this one for 4 meter. That is going to be 4 meter BC, and this guy gonna subject that to the uniformly distributed load of 2 kilonewton per meter. This is 2 kilonewton per meter. This is gonna be C. And the last one that we have is the 2 meter column CD. Okay, this is gonna be DC, and what we have is the area that we will use to draw the shear diagram, moment diagram of each segment, and after that you may need to combine them together. Okay, and what we have is 0.547. This is 0.547 kilonewton. 4.137. This 4.137 kilonewton. And this one 0.547. Again, this is 0.547 kilonewton. And this one is 3.863. Okay, this is 3.863 kilonewton, and then it's time to determine the end shear and end moment, and it's going to be very easy if you determine this. and this one upward, this one is downward, 4.137 kilonewton. You don't need to use the equation of equilibrium. If you prefer, you can do so, but if you use it, it's going to kind of mess up thing here, so I just neglect it. And this one is on the left to the right, this one is from the right to the left of 0.547 kilonewton. And then it also has the moment for sure. If you take the moment here, okay, you can see this guy will produce the moment in this direction. So this one gonna produce the moment in this direction to balance it. So if you do the summation of the moment at B equal to 0 in this direction, so our moment here gonna equal to 0.547, 0.547 times 3, and that is going to be 1.641. This is going to be equal to 1.641 kilonewton meter. Okay, and now this is joint B. You may prefer, if you like, to transfer the forces and no moment passing this joint, but most of the time you don't need to. If this joint have no force and no moment externally applied to it, okay, so if you know that this is going to be this way, and you may do it, you can do it as your homework if you like. We may transfer directly like this. This is going to be 0.547 kilonewton. This is down, so this is going to be up 4.137 kilonewton. And this moment gonna apply here. Okay, and if you like, you may put this one 1.641 kilonewton meter. Okay, that is for the point B. Now again here, 3.863 to be downward here, and then it's going to be upward here, and this is 3.863 kilonewton. 0.547. Okay, this is also 0.547 kilonewton, and it's going to be here. Okay, 0.547 kilonewton. And the moment, okay, this one going to have 2 meters, and this is going to rotate in this direction, so there is going to be the moment here, and the moment here we call it M sub C, summation of the moment, C equal to 0. Just take moment here, so 0.547 times 2, 0.547 times 2. And if you like, you put it into your calculator, and then you get this one for 1.094094 kilonewton meter. Okay, that is the end shear, end moment, and end axial force for each member. Now, if you prefer to draw this, you should start from the column, and also you may do the zooming on this. Okay, for this one, let me put this one. This is going to be the column, and then this is downward. So we have this X meter, and this one gonna be the shear kilonewton, and this one is 0 meter. This is 3 meter. Now this one is downward for 0.547. Let's see, 0.547, what the scale is supposed to be. if you like. Wow, let's say 5 millimeter per 1 kilonewton. Okay, if you like. This is going to be 0.5, right? And let's see this is just very small, and then this is going to be 4 point something. That's a lot. So just put this one only 2 millimeter. 2 millimeter for 0.5 kilonewton. So 4 millimeter for 1 kilonewton. So this is going to be about 2 millimeter. And then this is minus 0.547 kilonewton. Since W is 0, so the slope here gonna be 0, and you will get this in parallel like this. And this is gonna be minus 0.547 kilonewton, and this is put 0.547 up to close this, so this is negative here. Okay, and then we come to the moment diagram of this. Let's put this one is going to be negative because the dm by dx gonna be minus moment kilonewton meter, and this is gonna be 0 kilonewton meter because no moment apply here. And what we have is going to be dm by dx going to be equal to v minus 0.547. It's going to be something like this. And then it's going to be equal to minus 0.547 all the time. And the moment up here is what? If you put this one, so m plus 1.641 equal to 0. So this is going to be minus 1.641. Okay, that is going to be 1.641 times 4 millimeter. That is going to be about this. Then you have this. This is going to be minus 1.641. You don't need to put them in kilonewton because kilonewton is here already. Okay, and then this one going to close, and this one is going to be negative. Since this one is negative, so the deformation going to be concave like this, downward. Okay, that is for the column, right? So we move for the beam. For beam here, and for the beam, what we have is this one 4.137. If you use scale this, that is going to be a lot. A lot. And then the shear here going to be very large. It's going to be about 4 times 4 is 1.6 millimeter. That is going to be a lot shear. Use the scale, that is going to be about this. Okay, this is past 4.147, and if you prefer, the scale is no good, so this is V kilonewton. And again, this is 3.863. The duty this is going to push this one like this with 3.863, and you may see this is going to be minus 3.863 to push this one to the 0 here. Okay, so this is x meter and this is v. So we have up here, and then the dv by dx going to be minus 2, and then you will have the graph like this. This is 4 meter. You got this from 0. Okay, that is going to be the shear diagram. And what we have is, what the distance here is, what, 4.1 4.37 divided by x equal to 2. So this x equal to 4.137 divided by 2, and it's going to be 2.0685 meter. Okay, that is for this here is plus, this here is minus. And then we have the moment. Okay, moment again. And this is going to be the m kilonewton meter. And what we have is the direction of conventional m here. And what we have is what? This is going to the same direction. So this is 1.641 is going to be negative. Okay, this is going to be negative. Minus 1.641. Written here already. No way, it's that one. And then we have the dm by dx. dm by dx equal to v, 4.137. So this one is up. And this one, we have the shear here is 0, so the dm by dx equal to 0. And what is the moment here? We don't know yet. The m here. M here. Minus of minus 1.641. And then this one minus this one equal to the area here. Equal to 1/2 of 2.0685 and 4.137. And if you put them into your calculator, m here is going to be 2.637 kilonewton meter. Okay, so this is 8 centimeter, 8 millimeter for 1.6. This is 1.3. And if you prefer, you may put this one. Something like this. And this value gonna be up here. Okay, to make this thing go together. Now, about this, the moment, conventional moment here is this, and it's go the same direction as 1.094. So 1.094 is going to be negative, about 5 millimeter. This is going to be minus 1.094. And we're supposed to have this one, dm by dx equal to minus 3.863. And our curve gonna be something like this. Okay, and this is plus concave upwards. This is minus concave downward, minus concave downward, like this. Okay, and we have the last one for the column here. One for the column here, and again, this shear is upward. Let's say this is x meter. This is 0.547 upward. 2 millimeter. 0.547. This is V kilonewton. And then W is 0, so the dV by dx equal to 0. And then this one downward closes. Okay, and the last one, we have the positive slope. So okay, the moment here is 0 kilonewton meter, no moment. And dm by dx equal to plus 0.547. Okay, and you can see this moment and this moment is in opposite, so it's plus. So it's up here of what? Of this one. And then this is going to be your graph. Okay, and if you prefer, you set this one. Just put this one, this one, this one to indicate your slope, and this one, okay, also this one and this one to indicate your slope. And now for this, just put this one for the slope here, this one for the slope here, this one for the slope here. And for this side, this is for 0. And this is also for the slope. Okay, that's all we have for the shear diagram and moment diagram of this frame. And now you are ready to use it to draw the elastic curve. Okay, if you prefer to draw the elastic curve, let's put this on the bottom of this. Just we have 4 meters. Okay, 4 centimeters. We have 3 for the column. We have 2. This is A, B, C, and D. Subjected to vertical unit load of 2 kilonewton per meter. Okay, since this is I1, this is I1 also, and this is taller. Okay, so you can bend the taller column easier than you can bend the short column, right? So due to that, this guy will have the rotation like this, and this one supposed to have the side sway in this direction, and the B change to the B part. And now this point, they're going to keep the right angle. Okay, and this is follow this. For this one, this is going to have this kind of deformation. So this may have this kind of deformation, and also it's going to keep this right angle. Now what we have, this is concave downwards, concave upward. So this is going to concave, concave upward, and then it's going to concave downward like this, and concave downwards like this. And this is going to be the IP, the inflection point, okay, of this frame. And what do you have? This frame gonna say sway like this, and what we have, due to this no deformation, let's say due to very small, technically you may set it infinitely small deformation, small axial axial deformation of the columns and beams. So delta BH is equal to delta CH. Okay, this is going to be delta CH. They are equal. Also, delta BV is equal to 0. Delta CV also 0. So over here, we may have the slope, okay, of theta B. And over here, we have the slope of theta C. And this is theta A. And this is going to be theta D. So these are four slopes. We have four slopes to determine if you like. And the delta AH equal to delta AV equal to 0 because it's pin. Delta DH equal to delta DV equal to 0 because they are pin. Okay. That is the elastic curve. Of this frame. I cannot go back to draw over there. No, over here is a better that a little bit more easier. And then what we have is reinforcement. Okay, we have the beam, the frame like this, the beam and the column. Now, what we have is this one. So, for the positive, it's going to be like this. So, this one going to have the reinforcement, the extra reinforcement like this. This one is negative. Okay, and this one has the reinforcement on the right, and this one we have the reinforcement on the left. Okay, that's supposed to be the reinforcement. If it is the RC frame, this one is not, but if, okay, we do the practice. And you may know that usually we already have that. Okay, this extra reinforcement over there. Okay, it's depends on the detail of your reinforcement, but the main extra reinforcement for the corresponding to the bending moment is going to be like this. Okay, this is going to be the example that we have for the analysis of statically indeterminate rigid steel frame. And this frame have two columns and one beam, and the beam is stiffer than the column. The problem gives us this deformation or displacement in the horizontal direction already. So the problem is easy, but it's better for you guys to go back and trying to determine this. And we also have this for the f sub dd. We can determine by typical the method of virtual work that we have. Okay, please do the practice to determine actually this we call the delta dh. Okay, this is delta dh. And the other procedure, after you determine the f sub dd, you get your redundant force, and you apply the redundant force, you determine the reaction. After you get all the reaction, you can draw the shear diagram, moment diagram. Okay, after that you can draft your elastic curve, putting the reinforcement if this frame is the RC frame. Okay, let's do the practice. Do a lot. You will get more skill and more skill after you do more practice. And hope you guys will enjoy what's learning here. And please practice, and you will get the ending sense and ending judgment after you pay a lot of attention to this. Okay, that is the end of the clips. Okay, bye.